This presentation is the introduction to multi-position linear algebra library, MP Lapack. Okay, so here is the outline of the talk. What is and why MP Lapack? The availability of the package, other numerical multi-position libraries, and we're going to go through some examples, parallel processing, and I will make some comments on the limitations and point to the audience some references. So what is and why MP Lapack? MP Lapack is a rewrite of the widely used linear algebra package BLAS and the Lapack with multiple position support by Japanese scientist Nakata and Maho. It keeps the same interface of a BLAS and the Lapack routines. And the Lapack is for solving a linear system of linear equations, least squares problems, finding eigenvalues and eigenvectors, and computing a singular value decomposition, and so on, using a building blocks provided by the BLAS for dense matrices. Lapack and BLAS were written in Fortran, or as a matter of fact, in Fortran 77, containing various subroutines separately supported for IEEE, a single and double position for real and the complex matrices and the vectors. And the same routine, same interface, for example, GM and getTR with a different letter X in front as a prefix for different types. And there are needs from physics, chemistry, engineering, and mathematics where a higher position, especially the accuracy of hundreds of digits is wanted. So Lapack doesn't support arbitrary position. If one wants to solve, for example, conditioned problem AX equal to B, or compute eigenvalues, or solving positive semi-definite programming where higher position is desired, there is a gap between the needs for the linear algebra operations, Lapack, and the needs for higher precision. And the MP Lapack bridges the gap. So first example, solving an ill-conditioned problem, a linear equation, that's 2x2 linear equation. We construct the right-hand side by multiplying the matrix A by a unit vector. And we now revert to solve the vector X. So we, of course, expect the solution is the same as the unit vector. Now, we make some small changes in B, and we see there is quite different in the solution than the original vector X. And again, we make some changes in A, in matrix A, by less than 0.001, and we keep the right-hand side B the same. Now this time, the solution, again, there are large changes in the solution. So, as we see, small changes in B and A lead to big changes in the solution. This matrix is ill-conditioned. Things like this may confuse us in real life. So this raises questions, especially when we are facing real problems. How do we know the solution we have obtained is correct? And how reliable is the computer's solution if we have a small change in the input and we see a large change in the output, and so on? A second example, solving a system of linear equations where the coefficient matrix is Hilbert matrix, named after the German mathematician David Hilbert. And this is an example for matrix size of 6. Hilbert matrix is known to be very ill-conditioned when the size n is large. And solving ill-conditioned linear system can become problematic. The matrix may become singular in IEEE floating point position. This means when the machine thinks the matrix is singular, and there's no solution. And likewise, your program crashes. So continue solving the linear systems. As I said, Hilbert matrix is ill-conditioned, and the solving the linear system through the LU decomposition may become problematic when n, the size, becomes large. And here we show the results of solutions for different sizes, from sizes 10, 11, 13, and 50. And as we can see, when the size is greater than 12, one starts getting warning. If you want to solve this in MATLAB, the matrix is a singular to machine precision. So we will come back to this later. Now, the availability of this package, MP Lapack, and you can find the package on GitHub, and it is available for Linux, Mac OS, Windows. And the two methods for installing this package on your computer. The author recommends to use a Docker for the ease of installation if you don't want to do any extra work, and use Docker. And if you want to know how to use Docker, and you can Google it on the internet, or you can go to the Alliance, the website, the documentation to find how to use Docker or Aptainer. And we strongly recommend at the moment to install from the tarball on the GitHub rather than cloning the project on your computer. And as you might hit some bumps if you cloning the project instead of installing it from a tarball. But other than that, the installation on Linux is quite straightforward, and you just follow the instruction. But mind you, though, the building this package might take as long as 3 to 4 hours on your laptop or desktop. It takes quite long, quite some time to build. And the build package has a very well organized structure. From the inside the root structure, you have a bin, you have an include directory containing the head files, the header files, and the libraries, the shared and static libraries, and a folder called a share, and where you can find a lot of examples. The package comes with the user manual and examples in the share folder. And those examples are very easy to follow if you have used the Lapack or BLAS before. Supported the precisions. The following are the supported floating point formats: IEEE double position, extended the double position using 80 bits, binary 128 bits, or quadruple precision, equivalent to 33 decimal digits, double, and the support for arbitrary position using a GMP and MPFR for arbitrary position. And the position can be set by environmental variables, by these two environmental variables for GMP and MPFR position. MPFR stands for multi-position floating point reliable libraries. Okay, other related tools and packages. And here's a list of related multi-position packages in the systems. Of course, the first, the famous on the top is the Maple for symbolic or computer algebra computations, Mathematica, GMP, MPFR, and MP Fun 2020. This is multi-position library for Fortran and C++ as well. And ARP is a C library for rigorous and real complex arithmetic with arbitrary position. And the Julia is emerging program language for scientific and high performance computing with a lot of support. It supports the multi-position computation with the intrinsic data type for that. And the MP Math, this is interesting. This is a Python library for arbitrary position floating point arithmetic. And it claims it supports various linear algebra operations comparable to Lapack and the BLAS. Now, let's look at how MP Lapack works through some examples. This would assume that one has a basic C programming knowledge and some experience in using linear algebra packages, BLAS, and the Lapack. Now, let's take a look back at the previous examples, solving the system of linear equations where the coefficient matrix is an Hilbert matrix. We solve it in MATLAB or using a Lapack routines directly in C or Fortran. And we examine the relative errors for different size n. As you can see, when size is 10, the relative error is small. So that's okay, that's good. When n is 12, the solution is off, and we have a 50% of relative error. What does that mean? So what do you think if we get a relative error of a 50%? And to continue, with n is greater than or equal to 13, the solutions start going south. We got a 200.7% of relative error. And when n is 50, we got 2,700% in the relative error. So that's totally unacceptable. Now, someone may be aware that the inverse of Hilbert matrix has a closed form. And we could get a solution right away by multiplying the right-hand side to the inverse. True. But however, when n is greater than 12, some of the entries in the inverse cannot be represented exactly by the IEEE double position, and some small error may get amplified, and we lose the accuracy. And what you see here, is the display of the column, the 9 to 13 columns of the inverse of the matrix in order of 13 in Julia. And by the way, in this particular case, we used a special package called a special matrices in Julia, and the values here are represented in the rational format. Okay, the double slash signs and over 1 means this representation is in the rational form. It is not an integer and not floating point numbers, but it is in a rational format in Julia. Now, we used corresponding MP Lapack routine, RGESV, to solve the linear system. Now, by the way, the Lapack routine, GESV, is the routine to solve system of linear equations through LU decomposition. Okay, so what we do here, I just list the code in using a Lapack and the MP Lapack side by side. On the left hand side, it is the code using the Lapack routine, and on the right hand side is the code that is using a MP Lapack. So what we do first, we create the right-hand side. We create the right-hand side by multiplying the coefficient matrix by a unit vector. We're calling the blast routine GEM, G-E-M-M, GEM, DGEM. DGEM is a famous blast routine for matrix multiplication. So we're calling this routine DGEM to multiply the matrix by a unit vector to get the right-hand side. And then we call the Lapack routine GSV to solve back, this reversely, to solve for X to get the solution. And the GSV, in this case, we use the version DGESV, which is for double precision. It uses LU decomposition. So given the coefficient matrix, in this case, we plug in H, and the right-hand side of B in the calling sequence, and with some auxiliary arguments and work and the workspace, and we just solve for X, and the solution is stored in the vector B. Okay, and then we just print it out. And the same thing in MP Lapack, the calling sequence, the interface is identical except for the name. In MP Lapack, we replace all the prefix D, S, C, Z in the Lapack routines with a letter R. Okay, it is the same for any position. Regardless, we're using where we want a double position or single position or arbitrary position, and regardless, we're using the underlying multiple position library we're using, the interface is the same. It's always R, followed by the original Lapack routine name. Okay, that's the naming convention. And then let's take a look at the result. Here's the result for size 13 using 15 digits. Okay, the 15 digits, we set the position with environmental variable to 52. Now, what is 52 here? If you remember, in the floating point representation, we have the sum bit, we have the storage, the representation for real number, floating number in IEEE standard is we use a sum bit, and we use exponent component, and we use a mantissa. It is the mantissa that defines the position of the number represented in that particular position. And here, we're using a mantissa with 52 bits. This is equivalent to the IEEE double precision standard, and roughly converted to decimal point digits, we have a roughly 15 to 16 digits. And as we can see, the solution here, if you just look at the solution, they're way off the original vector, unit vector X that we use to create that right-hand side B. It's easy to see they're nowhere close to the original value. And therefore, the relative error is very high, it's 5.7, which means that's it's close to 600% in the relative error. So next, we increased precision to 64-bit, or equivalent to 19 decimal digits. Now, this time, we're able to bring the relative error down to a satisfactory level. This is pretty good. And then next, we increase precision to 100 bits, or roughly 30 decimal digits, and the relative error is unnecessarily small. So we can just stop there. Next, we increase the size to 50. And we use the position 64 bits, or roughly 19 decimal digits. The relative error is very big, 38, or 3,800%. And then increase the precision to 128 bits. The relative error decreases, but not a lot. And then increase it to 256, or roughly 77 decimal digits. This time, the relative error is small. Now we're okay with this. So next example, let's take a look at a different problem. And we're computing the eigenvalues of Wilkinson matrices. The Wilkinson matrices has this form. It's a tridiagonal matrix. If n, which is the size, is odd, then it takes the first form. If n is even, it takes the second form. And here we show the example for a size 7. We got the diagonal, we got the non-zero elements on the diagonal and the ones on the off diagonals. And we compute the eigenvalues of this matrix. And here we're looking at the Wilkinson matrix of size 50. Now, the interesting property of the eigenvalues of a Wilkinson matrix is they seem to appear in pairs. For example, we seem to have a pair of values of 21, the value 21. Now, to see whether we are actually having eigenvalues in pairs or just the illusion, we increased precision to 80 bits, or roughly 24 digits, to examine more digits after the decimal point. Now, after using MP Lapack routine STEV, STEV is the routine for computing the eigenvalues of symmetric real matrices. Okay, in Lapack. And we see, which is the output is very small in a very small file size, and I should magnify them, and you can compare the two. And as you can see, the two values, 2.1 or 21, after certain after decimal points, after certain digits, they start to differ. Okay, so using the MP, the multi-position version of a Lapack, we are able to compute things in a higher position. This is another example. And before, we're unable to do that with the Lapack routine. The traditional Lapack routine and the BLAST routine were written in a fixed position. There's no way to change that. Either you get the single position or double position. But with the MP Lapack, we have that barrier removed, and we can compute in any position we want. Next, let's look at the last example. Again, take the algebra matrix, for example. Now we are doing a common operation to compute the singular value decomposition of a matrix. In this case, again, it just shows an example of a size, the algebra matrix of a size 6. Now, for an n by n real matrix A, the singular value decomposition of A is a multiplication of 3 matrices, U, S, and V. U is the n by n square matrix, and the V is the n by n square matrix, and the S in the middle is an n by n matrix with the non-zero elements on the diagonal in two different cases. When the number of rows is greater than n, we have those values on the diagonal. They call the singular values. And and when the number of rows is less than the number of columns, and we have the singular values diagonals in the second form. Now, if you look at these two matrices S, it clearly tells us immediately the rank of this matrix. Okay, if there's the zeros on the diagonal, then we know that it is not a full rank. And among many things, one of the properties of the singular value is it can tell us the rank and the condition number of the matrix. For example, is it close to singular? So if we have 0 on the diagonal, or we have a value, the singular values, which is very, very, very small, then it is effectively considered as a singular, or it is a singular from the machine position point of view. So these are sort of the things that we've been looking for so far. And we can compute the condition number, measure condition number. It's a measure of how ill-conditioned the matrix is. And the condition number here, if you recall in the linear algebra, it is the maximum, the singular value. It is a ratio of the maximum singular value to the minimum one. You can see that in the MATLAB to verify that easily. Now, the use of the required MP Lapack routine is very simple. I just put the code snip here to compute. The routine, the Lapack routine we're calling is GESVD. And in Lapack, it will be called the DGESVD for double position. And for single position would be SGESVD. But for the purpose of computing the singular values decomposition, we always use double position. I will also use as high precision as we can. Okay, and here using an MP Lapack, we're using the routine with prefix R, RGESVD. We're passing those arguments, and then we compute the singular value we pass in A, and then we get the matrices S, U, VT out. And the work here, the third argument is a workspace required originally by the Lapack. Okay. So the calling sequence remains the same as the Lapack. For details, you would have to look up in the Lapack menu how to use those routines for particular problems, what Lapack routines to use, and how to use them. We need to have a reference menu in hand, just so that we can do things easily. Just nobody can remember the names and the calling sequence, especially the Lapack was written in 40, 50 years ago, and back in Fortran. Back then, there's a limitation in the number of letters in the variable names, in the function name, subroutine name. They're restricted to 6 letters and the digits. So some of the names totally make no sense to to people today. But so that's why we need a reference book. We need to look up, and that's how we use them. Nobody can memorize those any of those routines. Okay, so here shows the comparison of singular values and the condition numbers for open matrix of size 13 computed by MATLAB, and the use of RGSVD of MP Lapack. And the MP Lapack with the higher position by default, we're using 154 decimal digits in MP Lapack. MP Lapack gives a more accurate result. Okay, just quickly comments on parallel processing and the possible parallel processing. And currently, a few routines in MP Plus. By the way, MP Lapack comes with the two parts as the Lapack Plus and the Lapack. And MP Lapack has the components MP Plus. A few routines are optimized for accelerations through OpenMP. For example, XPY, or to compute the scalar multiplication to two vectors x and y, and store the result in vector y, and a copy an object from A to B, and a dot product of two vectors, and the gem matrix multiplication. Essentially, it performs the computation of scalar alpha times the matrix A times the matrix, I have a typo here, matrix A times the matrix B instead of X, plus a scalar times matrix C, and the result is stored in matrix C. Okay. To use the parallel feature optimized the routines, we need to compile and the link against the optimized MP Plus routine. With first, if we're using, this is an example of using a GNU compiler, we need to use an option F OpenMP, and we link against the MP library plus underscore MPFR. By the way, I didn't mention that. The MPFR, that's the underlying package used for multiple precision. It could be replaced by GMP, and it could be replaced by some other packages with the details in the manual. Okay, and here just an example using MPFR. And for parallel processing, we need to use the particular version OPT, optimized version. So the regular version, the library is compiled for computation without the parallelization, without acceleration, and other libraries without OPT. But the libraries, the versions of the library optimized for parallel processing and for acceleration are the libraries all have the name with underscore OPT, and also that's easy to memorize. Okay, and I don't have the results to show here because I just did the preliminary testing on my own personal computer. I only have 4 cores, and what I can tell you is the scaling from using 2 cores to 4 cores is a very is almost a linear. The time can be a cut to half, but I don't because I only have 4 cores. I thought that there's not much point to show. But if you want, we can do. I can do a live demo later on just to convince you if you curious to know. So that's about the parallel processing. Fairly simple and straightforward, and some limitations. And currently, it only has the CC++ or more precisely, it's a C-style interface. And there's a no Fortran interface so far. And setting the position is restricted by the underlying multi-position library packages. For example, GMP or MPFR. And sometimes the GMP or MPFR seem to be in favor of multiple of 32 when you try to set the binary position. For example, set to 32, set to 64. If you set something in between, it doesn't seem to work quite well as you expected. There's some limitations the underlying multi-position packages used. The third point is the data objects are opaque. So when you use the MP Lapack, you define your matrix vector as an object MP Lapack. And as to what exactly this object is stored is opaque to users. And therefore, the handler function for output are limited. So far you can only print the values of a matrix and the vectors in primitive format. If you want to do something fancier, you want to do, for example, you want to have a matrices and the vectors printed in a pretty format. It is hard because the menu doesn't provide more details on the underlying implementation. And lastly, the interlanguage operations requires some coding work. If you want to call MP Lapack from some other languages, for example, Fortran, it needs some work. If you want to call it from Julia, and also it needs some program work. Okay, lastly, some remarks. MP Lapack is a multi-position version of Lapack. It's just conclusion for linear algebra operations. It is callable from a CC++, but not readily from Fortran. But it has the potential being ported to other languages. And thanks to the design philosophy, it keeps the interfaces identical to original BLAS and the Lapack, which make things a lot easier, especially for those people who have been using BLAS and the Lapack in the past. And it is easy to install, and it is quite straightforward to use. And if one is familiar with BLAS or Lapack. And the key building blocks in MP BLAS are optimized and capable of performing parallel processing or with accelerations. And last thing is, in order to use it to get some meaningful results for your analysis, it is expected that you would have, one needs to have some knowledge in numerical analysis as a guideline. And one needs to experiment with the accuracy by setting the number of digits. Okay, I'll just put up the list of references here.